Hello friends, now let's discuss about staggered pulse repetition frequency. Basically, this is one of the other method to eliminate blind speeds. So how we will eliminate, we'll see. So basically, actually this is already happened the same way. We have changed the PRF and to find the unambiguous range. In our, I think it is the second video. I think so. To find the unambiguous range, we used this because if you had three different the targets, and so only the true frequency will be sorry, the true location can be revealed uh, by making use of changing PRF. The same way here also we are using the same thing. We'll change the PRF from pulse to pulse. It's called staggered PRF. Okay, like for first pulse it will be one PRF, for second pulse it will be second PRF, like that. So the use of multiple waveforms with different PRF allows the detection of moving targets that would otherwise be eliminated with a constant PRF waveforms if the radial velocities were at or in the vicinity of a blind speed. So within that blind speed only, if the velocities are there, we can uh, we can eliminate this blind speeds. Okay. So how will first how will see? Let's see. I mean, even if you are not eliminating blind speeds, even if they are moving in blind speed, also we can detect. So, for the first frequency, the dotted line. Here we can see it is going down and coming up, right? So, at this point, actually, it can't. The speeds at this point we can't see, and also here like this. At the second pulse, we can't see here and here. But what happens? We are using two different frequencies. When this first frequency at f2 or the second frequency is f2, that means the blind spot is occurring, but still the first frequency has the is not going to be zero here, so that's why it can be detected. Again, even if the first frequency is going to zero, the second frequency is still having the peak, like that. But after doing so, after at some point at 2f1 is equals 3f2, we are again with these two are overlapping. That means we are getting first blind space. That means we will get one, even though we will get some first blind speed, but basically we have see, we have already removed three, right? So basically it will give the better results. Instead of using only single PRF, it will definitely will give better results. Okay, after some time you are able to see the blind speed. After a long time you are able to see the blind speed. Okay, so all these are it's fine, like even if f2 is at the blind speed but f1 is not, right? So it will detect the target, like that. So at this point where 2f is equals to 3f2, like in this example we are telling, that's it, like to understand how it works. So in this example, at 2f1 is equals 3f2 point, we are having this first blind speed. Okay, so so if you are using more PRF, we will have this value at somewhere. Okay, it will be difficult. Uh, Sorry. So when we have more PRF, then we can get more close. Okay. So even though we have blind speed, if even the vehicle is traveling blind speeds, the target can be detected because we are using different PRFs. So the PRF can be changed by using scan to like basically we are telling, no, pulse to pulse. Like for one pulse it is one PRF and the other pulse is PRF. So basically it is not the fixed. We can change for scan to scan, or we can use a dual to dual, that is on time on target, or we can also change the pulse to pulse. When if you change the PRF for pulse to pulse, it is called staggered PRF. Okay, so here we can see there are using staggered span of four different pulse periods. At initially it's T1, from here it is to here T1, here T2, T3, T4, again T1, T2, T3, T4, like that. The filter samples the Doppler frequency at non-uniform time rather than uniformly spaced time samples when the PRF is constant. So basically, what we are doing, basically this filter samples the Doppler frequency at non-uniform times. Okay, So now, like for example, see, you can see it is non-uniform only, right? Instead, previously, if there is not change, there is no change in the PRF. That means every pulse will be the same frequency. Then all will be in equal spaces. So equal spaces, that means it is uniformly spaced. But now the filter has to filter the symbols at non-uniform spaces. That's it. You understand that? So here it has to first, it has to filter T1 and it has to filter T2, T3, T3, all are different values. Previously all are same, no? So every time it will, for example, for example, uniform space by 3 seconds. Every time at every 3 seconds it will sample, but now it will have to sample at different frequency, different time intervals. So therefore, the frequency response of this filter will be h of f is equal to w naught. So w naught, w1, w2 are the weights actually. So that means constant, normal constant. So this constant can be anything that you should choose properly. So omega w naught plus w1 into e power j 2 pi of t1 plus w2 into e power j 2 pi of t1 plus t2. So basically the time delay should be added. Same like how we have used the delay line canceller. Same way. There also we have seen weights, and also that time delay has been increasing. Now, the selection of that n plus 1 weight Wi and the n pulse repetition period Ti is generally constrained by several design factors. So basically, how to choose all these Ti and Wi values are based on these six. Okay, uh, based on these 6 factors you need to. So first is the minimum period should not require the range ambiguous. The minimum period should not result in range ambiguous. That is, no, an ambiguous range and ambiguous range. So ambiguous range means still, if you ambiguous range means if the target is at 10 meters, but that radar is detecting it as some different 5 meters like that. It is an ambiguous. So, and that should not happen, and the sequence of the period should be selected so as not to stress the transmitter by employing a widely varying duty cycle or a duty cycle for which the transmitter is not designed. So the duty cycle should satisfy, like whatever the radar or antenna is designed for a particular duty cycle, that should satisfy by this equation. Okay, when you design this filter, this should satisfy the duty cycle as well. Now, maximum period should not be long, since any range beyond the maximum ambiguous range can't be detected, right? So that's why the period should also be should not be too long. So, and if it is too long, we can't detect the targets. And the response in the filter stopband should produce the required MTI improvement factor for detection of targets in cluster. So it should the stopband of this response should produce the required MTI improvement factor. That improvement factor we see, so that should be like basically we'll calculate some value. So we should get the same required value here also with for that particular stop band. The deepest null is the deepest null in the pass band should not be excessive. Usually the deepest null occurs at the frequencies equal to the inverse of the average period. So basically the deepest null will occur at the frequencies 1 by t average. Like the frequencies, when the frequency is equal to 1 by t average, there the deepest null will occur. Okay, wait, I'll see whether it is. So the deepest null is the pass band would not exist. So basically the null is called or the null in the radar system, what it means was, when this condition occurs where the frequency equals to the 1 by t average, the detection accuracy of the target will be decreased. Okay, of the system radar will be decreased. That's why that he is saying that it should not happen in such case. The deepest null in this passband should not be excessive. Usually the deepest null occurs at the frequency equal to the inverse of the average period. Okay. The variation or the ripple of the response over the passband should be minimized and relatively uniform. The passband should be minimized and relatively Okay, even if the variation of ripples are there of a response, okay, this is a frequency response, right? We'll get ripples like it's like a waveforms, like see, like this ripples. So that should be uniform. Mm. In not all the above conditions can be satisfied simultaneously. Design of a staggered PRF, it is and its operation and its processing is often a compromise. So we just compromise with some in the out of six we'll just compromise some values, some statements. Okay. Although the staggered PRF remove the blind speeds which should have been obtained with the constant PRF. That means if you use constant PRF, there will be blind spots, right? It will remove those if you are using variable staggered PRF, which will eventually be a new blind. Basically, as I told, there will be anyways at some point there will be one new blind spot. But okay, but it will be at some far. This will eventually be a new blind spot speed that occurs when NPRF has following relationship. Okay, so basically there now we have to calculate the the relationship between the okay wait so the relationship between with constant between the PRF sorry the blind speeds occurred for staggered PRF, that is let us take a V1 which is the staggered PRF the blind speed of staggered PRF, or the first blind speed, sorry, V1 is the first blind speed occurred for staggered PRF, and VB is the wave blind speed occurred with the constant PRF. So uh, so first we are taking the condition that n1 we are taking n PRFs. Okay, with n PRFs n1 f1 is equals to n2 f2 is equals to n3 f3 so on n fn. So this condition should satisfy where n1, n2, and nn are the relative prime integers, prime numbers actually, with no common divisors the other like 2, 3, 5, 7, 11 like that. So here the first blind speed of V1 with the staggered PRF waveform occurs at the following Doppler frequency. So Doppler frequency FD1 can be occurring at N1 F1, N2 F2, N3 F3, Nn Fn all should be same. So that product value is the FD1. Okay, N1 and N2 are the mutual prime numbers. Now V1, that is the blind speed of at staggered PRF. Lambda by 2 N1 F2 is equals to lambda by 2 N2 F2 is equals to so on, where Vn is equals to N lambda by 2 Fp. That means lambda by 2 into NFP, where how we wrote. Okay. Now Fp is precipitation frequency. Next, the first blind speed Vb of a waveform with constant PRF should whole period is average period. Basically, now we are calculating the average time period for a constant PRF. The T average is equals to 1 by n into T1, T2, T3, so on Tn. Ti is equals to 1 by F occurred at Doppler frequency FD1, FDB. So basically B in the sense only constant PRF, that means FDB you are writing. FD1 if you write means it is for the staggered PRF, first blind speed of staggered PRF. So FDB is equals to F average is equal to 1 by T average. So basically in the previously what for a staggered PRF first blind speed the Doppler frequency is FD1 is equals to any of the product, that N1 F1 or N2 F2 like this. Here FD is the here Doppler for a constant PRF Doppler frequency is F average. That's why we calculated first the T average, then from that we can calculate T F average. So VB is the same as here also. VB is equals to lambda by 2 F average. Okay, so lambda by 2 into n by T1 plus T2 so on Tn. So basically now we are using the ratio of V1 by VB. So when we do the ratio, we are getting this n1 plus n2 plus n3 so on nn by n. Okay. So actually it will get like f1 by f1 plus 1 by f2 like that, but each one every frequency can be written as like in terms of f1, right? Because those are equal here. We are taking the condition like this. So if for example if you take this ratio, f2 can be written as n1 f1 by n2, f3 can be written as n1 f1 by n3 like that. We changed and all f1s are cancelled out. We left with this. Okay, so this is the frequency response of a 5 pulse stagger. Now this is the example of a frequency response of a staggered MTA with 4 periods of S band. We are taking 4 PRFs. Okay, this is okay 5. This has 4 period. This is also 4 period. 5 pulses. Okay, like this. And this is one more frequency response of weighted period staggered waveform compared with the frequency response using constant PRF. Dashed curve, constant PRF, solid curve, staggered PRF. So dashed is the constant PRF. If you are using constant, it will be this this keep it will go. Okay. When you are using that means what at these points we are able to see this one, right? What you call blind speeds. But see, if you observe for the dash stagger PRF, there is no like such. They are all getting. We are not able. We are not getting any blind speeds for this stagger PRF. So that's why we're going with the stagger PRF here. So the null depth and improvement factor. So the null depth and improvement factor, that is Imax is the improvement factor. The maximum improvement factor is equals to 1 by 4 pi square sigma n square sigma c square sigma n square. Sigma c square is the total variance of a Gaussian cluster spectrum. Sigma n square is the mean square value of a En, that is Ti minus T average. So Ti is the period of the ith stagger. T average is the average value of the n periods. That is the Imax. The depth, the null depth. Okay, the depth of the first null is n depth is equals to this. Okay, 1 minute. So that the depth of the first null is the null depth, that is 40 times of this 40 times sigma n by TAV whole square. TAV is the average and the sigma is the mean actually mean value. Sigma square is the mean square value of En, right? So from that we can find sigma n, or we can directly write this as sigma square itself. So sigma square is directly mean square value of En. Okay. So basically this is the graph between maximum period by minimum period where on the null depth. So approximate depth of the first null in the frequency response of a pulse to pulse staggered PRF MTI as a function of the ratio of the maximum period to the minimum period. So thanks for watching. In the next lecture we'll see what is the MTI for a moving platform.